All right, folks, welcome to this other set theory lecture. I decided to be more comfortable in my rocking chair next to the fireplace. So hopefully that's going to make those lectures even more lively. Okay, so let's get started. Today we're going to look at ordered pairs, the Cartesian products, and we're going to talk about relations a little bit. And in particular, we're going to look at equivalence relations. But really the core of today's lecture is the Cartesian product and ordered pairs. So we've already looked at this idea of an unordered pair in set theory where we have between curly braces two elements that are listed, which may be, elements, or they might be sets themselves as guaranteed by the pairing axioms. And we've also looked at cases where we could have more than two objects together in a set. So when we have things like that, they're called unordered because it doesn't matter whether you write A comma B or B comma A, right? This is the same thing. But very often when we reason about things, we need to take order into consideration. The order very much matters, right? So if you um, if you try to drink from a bottle before opening it, it really doesn't matter. It doesn't work too well, right? So you need to first open it and then drink from it. So the idea of an ordered pair is going to be our first step toward understanding what's happening there. So there are two avenues that we can pursue in order to introduce new kinds of sets or new constructions involving sets. So the first one is going to be um, um, as we did for unordered pairs, unions, and power sets, we would need to introduce a new axiom that guarantees that the construction that we are thinking about is indeed legitimate. And the second part is, well, maybe we don't need to introduce a new axiom because in fact, we can show on the basis of axioms that are already there and more or less clever maneuvers that, yeah, based on what we have, the construction in question is already implied to be legitimate. So which one is it going to be here? It's going to be the latter. So we don't need to introduce a new axiom to talk about order, despite what perhaps you might think at first. So the question that we're going to want to ask is, well, if if we want to talk about order, how are we supposed to be able to do that based on the principles of set theory that we already have? Uh, at first, that might seem like it's going to be problematic because we have the axiom of extensionality that tells us, well, a set is determined by its members, so that if you describe the set extensionally, it really doesn't matter in which order you're going to list the elements, right? So if we want to find a way of talking about order with the principles of set theory that we already have, we're going to have to find a way of expressing the concept of ordering in terms of set membership as we have already introduced it. So just consider the following ordered sequence where C is the first element, D is the second, B is the third, and A is the fourth. Now, the trick that we're going to use here is precisely this. For each position in the ordered sequence, we're going to form a set that includes all the elements that occur previously in the sequence. Right? So since C is the first element, the first set we're going to construct contains C. Since C and D are in this set, that will express the fact that D is the second element of the sequence. Here we have C, D, and B, which is associated with the fact that B is the third element of that sequence. And finally, we have the quadruple with A, which corresponds to the idea that A is the fourth element. And that's kind of clever. That's known as Kuratowski's trick to introduce the idea of ordering in set theory. So here's an example of how that trick is supposed to work. So here I have a collection of sets, right? It contains 1, 2, 3, 4 sets, right? And for each set in that collection, A is contained, right? So A is here, A is here, A is here, and A is here. So since A is in every single one of the sets in the collection, that will correspond to the claim that A is the first element in the sequence. Okay. Now we're going to take the collection and we're going to remove the singleton A from it. So C minus singleton A is going to give us the set that we started from minus this element here. Now in this new set, we have the pair, the triple, and the quadruple. We look for the object that's in all three, and that object is going to be C, right? So that tells us that C is the second one. Now we're going to take the collection. We're going to remove singleton A, and also the set that contains the first and the second element, so that's the pair AC. And only the second and the fourth element are going to remain. And we're going to see that D is in both of them. Oh, I made a mistake here. I wrote DACD. It should be BACD. My bad. But D is going to be the third object and B the fourth object. Right? So you see how we can reconstruct an idea of order based on what we already have using that. And this very simple idea or motivates the following definition for what it is to be an ordered pair. So an ordered pair whose first element is A, or first coordinate is A, as we often say in geometry, and B is the second element or second coordinate, and we denote such a pair in this way, where now we don't use curly braces to surround the list. We use another symbol. They are called the angle brackets, right? So we have AB between angle brackets. That's the ordered pair containing A as first element and B as second. That's going to be identified as that set whose first element is singleton A and then containing the pair AB, based on the trick that we just saw before. Often, instead of the angle brackets, parentheses are used in order to denote ordered pairs. The two notations are completely interchangeable, so you really can just use the one that you happen to prefer, but angle brackets are kind of nice, I think. Now, we're going to use that definition to prove one important property of ordered pairs based on that definition. But you're going to see that this is extremely annoying and extremely cumbersome. So as soon as we have proved that property, we're going to forget about that completely, right? We're just using that definition to show that talking about ordered pairs is already legitimate given the axioms of set theory that we have, so that we don't need to introduce a new axiom. But really, we're going to want to move on from there. So the theorem that we're going to want to prove is that if a pair containing A first and B second equals a second pair containing C first and D second, that happens if and only if A equals C and B equals D. So for two pairs to be identical, it has to be that their first member is the same and that their second member is the same. Okay, that's the idea. That's what we're going to try to prove. And that's really the only important thing that we need to know about ordered pairs. So we're going to prove that. It's going to be long. It's going to be annoying. It's probably the most annoying theorem of this entire course. Okay, we're going to prove that, and then we're never going to return to it. And In order to prove that theorem, we're going to use a few things that we have looked at before. So you'll remember example 5.3, which was one theorem talking about singletons and pairs. That's something we looked at immediately after introducing the pairing axiom. And we saw as we were working on that example that suppose we have a set that contains A, then we'll say A is in A, or whether A is a singleton or a pair. Furthermore, we had a rule that tells us if A is in singleton C, that must mean A is the same as C. Okay? So we saw that already. Then in example 5.3, the theorem we proved is that if the pair containing A and B equals the pair containing C, that means A equals B equals C. And you've reused that particular theorem, hopefully. If you didn't, that must have been really long to do. But I hope you did reuse example 5.3 when you were solving exercise 5.10, which is just a particular case really of example 5.3, which says that the following set here, whose first member is singleton A and whose second member is B comma C, equals singleton C if and only if A, B, and C are equal. Right, so that's the same as what we had in example 5.3, except that we replace A by the set singleton A, we replace B by the set, which is the pair containing B and C, and we replace C by singleton C. Right, so it's just a particular case, really. And another one that I don't remember if I drew attention on it for you when we were covering that, but just in case, here's the idea. Um, the idea is that if we've already proved that A equals B, and then we remove C from A and we remove C from B, the result's going to be the same, right? So if you start from two equal things and you remove the same on both sides, it gives you the same thing. So we're used to doing that in arithmetic. That works with sets as well. So again, I'm not sure if you have proved it or not, but it's exercise 5.15 part 7. If you want, I'll invite you to go back and look at it. It's fairly easy to prove, and in any case, a very intuitive theorem. I should say the proof I'm going to show you on the next slide is based on a Fitch diagram. It is in fact much simpler than the one I wrote in the notes, so I probably will go back and edit the note and give that simplified version that I came up with as I was preparing those slides. Okay, so let's look at this. So that's a huge proof, as you see. For this proof, it might be a little bit hard for you to see, but there's a little bit of a space between line 14 and 15. We're supposed to have two subproofs where the cut is in the middle here. It's just hard to see because I had to shrink it so that it would fit on one slide. And for that proof, I mean, we're gonna power through it. I don't think there's anything particularly deep about it. It's just annoying little details, and there's nothing important to learn from it in terms of learning how to do proofs. So let's just look at it. You know, it has to be done, and then we're never gonna look back. So I'm just doing the part that goes from line 1 to line 21. For the other direction, in fact, that one is fairly easy. So we're just going to focus on that one direction. So we start from line 1 saying the pair AB equals the pair CD. So that's our premise or our supposition. And we're trying to reach the conclusion that A equals C, so they have the same first member. And furthermore, B equals D, so they have the same second members. And for this one, I would tell you let's work backwards, but really the core of this proof is a proof by case. And in order to see how to set up the proof by case, we're going to have to do a few steps of moving forward. You're going to see. So by virtue of the definition of ordered pairs, line 1 happens to be equivalent to line number 2. That's just by definition. So we apply that definition here. Now, as was done in exercise 5.10, we can easily see that singleton A is in a set that contains singleton A. That's easy, right? We could show that without any gap, without anything missing, really following the deduction that was done in exercise 5.3 or in exercise 5.10. But really, I'm going to assume that it's work we have done, and that, I mean, in any way, it's pretty clear, right? That singleton A should be in a set that contains singleton A. So let's just assume it, and let's not be distracted by the details here. Similarly, it follows on line 4 that singleton A has to be in that other set that the set on line 2 is equal to, right? So on line 3, we say singleton A is in some set. Now that set equals that other set. Therefore, singleton A is in that other set. And then by virtue of the membership condition for pairs, it follows that singleton A equals singleton C, or singleton A equals the pair CD. So let's start with the first disjunct, and now we're doing a proof by case. And of course, the last line of our subproof for both parts is going to be what? That's going to be the conclusion that we keep carrying with us within the proof, the various cases of the proof. So from line number 6, it follows directly that A equals C. That's kind of stuff you did without gaps in exercise 5.10. So that's already, line 14 should say A equals C and B equals D. So from line 7, you already get the first part of line 14 if it's written without typos. But then we have to work a little bit more to get the second part. Wow. Line 13 should be B equals D. That's pretty embarrassing. How could I miss all of that? Because line 13 is supposed to be the second conjunct of the sub-goal. But in order to get to line 13, which is our second conjunct, the second sub-goal, we're going to need to do a little bit of work. And that's going to be based on the exercise 5.15 that I was pointing you to. Now, if we have line 6 or 7, whichever you prefer, it will follow directly that singleton A is the same as singleton C. If A and C are the same, those two sets should be the same. So that means that we can take line 2, which is that here are two sets that are equal, and we'll remove the same thing on both sides. But on one side, we'll remove the left-hand side of 8, and on the right-hand side, we'll remove the right-hand side of 8. And that gives us line number 9 in virtue of exercise 5.15 and lines 2 and 8. So that gives us, so take the first set here, remove singleton A. What's left is singleton containing the pair AB, and on the other side, what's left is singleton containing the pair CD, and that means that pair AB equals pair CD. So if we want to work all the details, without any gap, we would need to add a few lines here, but I think at least intuitively that should make sense. And if you want to work out all the details, please go ahead. But I thought it was long enough as is to fit on a slide. So we have AB equals, the pair AB equals the pair CD. And now we're going to take those two sets and we're going to notice A equals C. So I'm going to remove singleton A from one side and singleton C for the other, which is good because singleton A and singleton C are the same. So we'll remove the same we're removing the same from both sides. And that time it's going to give us singleton B equals singleton D. So on lines 13, we get B equals D, right? It should be B equals D. And that completes the first case. And then for the second case, we have A equals C, the pair CD. And really to get to our conclusion, we just straightforwardly applies what we have done before. Uh, so, so directly from line 15 to line 16, that's a particular case of exercise 5.3. Just replace capital A by, no, sorry, just replace capital C by A, replace capital A and capital B by C and D respectively, and that's what you get. Now, applying exercise 5.10, where you proved if and only if, from line 16, line 17 follows directly. And now the left-hand side of the equation on line 17 equals the left-hand side of the equation on line 18. That's what we have on line 2, you'll remember. And therefore, what do we get from line 18? Again, we just apply exercise, should say 5.10, sorry, and you get A equals B equals C. That was in fact exactly exercise 5.10. That's why I asked you to do it back then so that this proof might make some more sense. Okay, so now we have A equals C equals D and A equals B equals C, and of course that gives us A equals C and B equals D, and that gives us our conclusion. And now you're like, ah, what a nightmare. I don't know if you think that, but it's a little bit of a convoluted proof. If you were to try to do it with a pitch diagram without skipping any step, it would be so long and annoying. But now, hopefully that's okay. Okay, so that tells us the main property that there is to know about ordered set. Now we're going to move slowly from there to Cartesian products. So suppose we take two sets, A and B. We could form various ordered pairs whose first element is in set A and second element is in set B. And the question we want to ask here is there a set that contains all the possible ordered pairs that we could pick by taking the first element from the set A and the second element from the set B? And the answer is yes, there is one. And it's fairly easy to see. So let's start with two elements, small a from set A and small b from set B. Now, it follows that singleton A and singleton B are both a subset of the set A union B, right? That follows directly from what we have already seen about singletons. Now, furthermore, oh yes, sorry. So furthermore, what we've sorry, on the second bullet point, what I wanted to write is singleton A is in A union B, and then the pair containing A and B is in A union B. Because then, just by the membership condition of power sets, we get that singleton A and pair AB are both in the power set of A union B. Okay. So now if we take those two sets that are in the power set of A union B and we form a set containing both of them, that set is going to be a subset of the power set of A union B, which means that as a result, it's going to be in the power set of the power set of A union B. And that just means this last line, that the pair that contains A as first member and B as second member is in fact a member of the power set of A union B. Okay, so that says that this power set of A union B contains every single pair whose first member we pick from the set A and second member we pick from set B. Okay, so that set that contains all the pairs, We don't need a new axiom that tells us that it exists. It already follows by the union set axiom and from the power set axiom. Now, for those of you who know a little bit about functions already and about how important ordered pairs are to talk about function, now we see just how important the concept of power set and union is in order to explain the foundations of the concept of function. Okay, now this set, power set A union B, will contain, as we saw, all the ordered pairs whose first member is in A and second member is in B. But it might contain all sorts of other things. In fact, if you were taking a simple example and write it out explicitly, you would find that there's a bunch of things there that are not even ordered pairs. Okay? So what we're going to do is we're going to take that pair and we're going to add, not that pair, that set, and we're going to apply to it the axiom of separation to get as a result a set that contains every ordered pair whose first member is in A and second member is in B and nothing else, right? And that set is going to be called the Cartesian product of A and B. Now, why is it called the Cartesian product? I'm glad you asked. That's a very important question. Well, Cartesian, you see, comes from the name of some person called René Descartes, who is not only the founder of modern philosophy, as some people like to say. I don't like to say that, but some people like to say that. But he's also the inventor of modern analytic geometry. And the geometry that you've learned in school, where we have a plane with two axes called a Cartesian plane. When we pick a point there, it's going to have two coordinates that are going to be written either between parentheses or between angle brackets. So that's where this idea of calling that the Cartesian product, that's where it's coming from. Okay, so here's what the Cartesian product is. You take A and B to be any two sets, and we want to form the Cartesian product of the set A and B, which is denoted A cross B. That set is going to be the set of all the ordered pairs in that set, which contains all the ordered pairs, right? It's going to contain all those pairs such that A is in the first set, the left-hand side of the cross, and B is in the second set, the right-hand side of the cross. So the membership condition, because of the way we just defined the Cartesian product, the membership condition is going to be like that. So an ordered pair XY is in the Cartesian product A cross B, if and only if X is in A, the first set, and Y is in B, the second set. When A equals B, that is to say, when both sets forming the product are the same, instead of writing, say, A times A, we often write A exponent 2, which is, again, fairly standard. You might have seen R2 in geometry to denote the Cartesian plane where both axes are formed with the real numbers. That's the same idea. Now, if you want Fitch rules, which are often convenient, to organize all the things that are important about Cartesian products and about ordered pairs, we get the following rules. So you see, we have two rules corresponding to the membership conditions of Cartesian products, which I denote MC cross. And then we have two rules for ordered pairs, which summarizes that long and annoying theorem that we have looked at. Okay. Now that we have those rules, we can completely forget about that annoying definition of ordered pairs and just work with them in the way it was intended. Okay. So let's look a little bit at an example of what a Cartesian product could be. So take the set S that contains 4 elements, and we're going to form all the possible ordered pairs, right? So of S2, so S cross S. And that means that we're going to have as many pairs as it's possible to form combinations where the first object is picked from S and the second object is picked from S. So it's like forming a big truth table where we have um, 4 different variables. So we have AA, AB, AC, AD, BA, BB, BC, BD, all of them. Right, so if we have a set S that contains 4 elements, S cross S is going to contain 4 times 4 elements, which is 16. That's what we have here. So you see that, we multiply the numbers of entries in each set, which means that we're going to have really large sets again when we are dealing with Cartesian products. Not as large as those we had when we were dealing with power sets, but still pretty large, which is why very often we use a more abstract shorthand notation instead of describing those sets extensionally. Now, there are many important theorems about Cartesian products and how they interact with unions and intersections and differences and things like that. I've listed a few of them right here on that slide. So here's one that's interesting. If you take all the ordered pairs whose first member are in the set A union B, and the second member is in X, that's the same as if you form all the ordered pair whose first member is in A and second in X, and then take that and add to them, forming the union, all the ordered pairs whose first member is in B and second member is in X. You have to prove that in this week's homework assignment. The second we're going to look at on the next slide. The third is, well, suppose you start with a set A and you remove all the elements of B from it. And then you get some elements left. And then you form all the ordered pairs, picking the first object from what's left and the second from X. Well, that's going to be the same as if you form all the ordered pairs that come from picking the first element in A and the second in X, and then remove from that all the ordered pairs that you could form by picking the first element in B and the second in X. Easy. If A or B is empty, then the Cartesian product is empty. That's fairly obvious too, I hope. And if A and B, if the Cartesian product of A and B is non-empty, then we have the following, that if A is a subset of X and B is a and B is a subset of Y, then it follows that the Cartesian product A cross B is a subset of X cross Y. I hope all fairly intuitively true theorems. Let's just see how we would prove the second one with a Fitch diagram. Might give you a few cues and hints about how to tackle the first one in your homework assignment. So since we're trying to show that two sets are equal, the first idea that we might want to do is to show that, well, the left-hand side is a subset of the right-hand side and vice versa, that the right-hand side is a subset of the left-hand side, which would require you to do a Fitch diagram taking an arbitrary object C, which is in the left-hand side, and trying to show that it's in the right-hand side as a result. That would be for the first direction, right? Now, if we look at the first line, we see that the main operator in the set is the Cartesian product. So since we have a Cartesian product, we know that all the members of that set that we're talking about on line 1 are going to be ordered pairs. So instead of supposing that C is in that set, I suggest that you write explicitly the arbitrary objects as being an arbitrary ordered pair. Okay, so that's what we get if we do that. We suppose the arbitrary pair of objects CD is in that Cartesian product, and then lower on line 10, we conclude that this arbitrary pair of objects is in the intersection of two Cartesian products. Okay, and then you can work backward or forward. I mean, both are fairly easy. So I suggest we just work forward because that one is really, really easy. So since this pair is in this Cartesian product, the membership condition tells us what C is in the left-hand side of the Cartesian product, A intersection B, and D is in the right-hand side of the Cartesian product, which is just X intersection Y. Okay, so do a conjunction elimination that gives you C is in A and B, which of course by membership condition of intersection tells you C is in A and X is in B. Do that again for the second conjunct. So D is in X intersection Y, from which it follows that D is in X and D is in Y as well. Easy. But now you have the following. You have C is in A, and furthermore, D is in X. So by membership condition of Cartesian products, that tells you that the pair CD is in A cross X. Furthermore, you have X is in B and D is in Y. Membership condition tells you the pair CD is in B cross Y. Easy. Okay? But since CD is in both of those sets, that means it's part of, okay, here I formed the conjunction, sorry. And I forgot that C should be a CD, a pair CD. So you form the conjunction, and then that's just the membership condition for the intersection. So that one is not so difficult. Now, why are we talking about those ordered pairs? Well, that's going to be extremely important. I mean, at this point in our course on set theory, we really haven't reached a lot yet of why are we learning set theory? Why is that so important to learn set theory? Well, to talk about set theory in a way that is useful, we really have to make it the point where we're talking about functions. Functions are really important, and set theory give you the foundations for all of that. But they also give you the foundations for uh, the logic that we've already looked at. So in a way, we've developed predicate logic and the axioms of set theory that we've looked at in a way that is as intuitively clear as possible, right? We can already say that all the principles we've been using are correct. So the sentences we claim to be true were true. The argument forms that we claim to be valid are valid. And yet, there are many questions that remain unanswered, right? So showing that arguments are invalid is a little bit harder. Um, we haven't talked about the nature or the meaning of predicates and relation symbols yet very much, in fact. Right? That's what we would revisit after we acquired a certain level of set theory, because set theory is precisely the tool that we need in order to articulate a formal characterization of the semantics of languages that incorporate what we need to do predicate logic. So the idea ultimately is to revisit all the logic that we've already studied after we've used that very logic to learn set theory, and then we're not going to change what we said. We're just going to make it sharper, crisper, and add a deeper understanding of it. But in order to do that, we need to keep going a little bit because we need the concept of functions and the concept of induction. Now, the concept of function is going to be addressed in the next lecture, directly building on the last few things that we're going to be discussing today. Okay, but let me give you a little bit of a glance of what that general picture of what the formal foundations of the semantics of predicate logic would look like. So we have a language that contains all sorts of expressions. And the idea is that we use this language to describe a universe of discourse, to say what is the case, right? Determine, identify what is factual, and say, those things are true, and make inferences on the basis of what's true. And then we saw that there are a few main kinds of symbols in predicate logic. We have singular terms. Those singular terms refer to objects. Now, what are those objects going to be when you think of it in terms of set theory? Well, objects are merely going to be elements of D, where D is the domain of discourse. Right? Predicates are going to be assigned properties. Hmm? Uh, so the words to be read expresses a property, namely the property of being read. So in set theory terms, what corresponds to a property? Well, uh, properties can be thought of extensionally as in terms of the objects that have that property, say the read objects, right? So then we see that a property, or at least the extension of a property, can be associated with the set of objects that have the property in question. And that set is going to be a subset of the domain or the universe of discourse. And then for the relation symbols, so far I've often said relation when we were doing predicate logic, when really what we were describing were relation symbols. But relation symbols refer to relations in the same way that predicates refer to properties. And then those relations are going to relate n objects together. So in terms of set theory, what are those relations going to be? Well, they're going to be sets of n tuples. So n tuples, as we'll see later, are a generalization of the idea of an ordered pair, except that we don't just order two things, we order n things. Right? So binary relations will correspond to sets of ordered pairs, which are subsets of the domain cross the domain. So subset of the Cartesian product of the domain with itself. Now, when we have that, that's going to allow us to strengthen the foundations of logic, because we're now going to be able to quantify over all properties and relations. Right? So when we were looking at questions of validity and invalidity in predicate logic, sometimes I would ask you questions of the sort, hey, can you find an interpretation of that relation symbol such that this sentence is true and that one is false? Huh? And if you could come up with an interpretation like that, then it would show that the argument from the first sentence to the second is not valid. Right? So I'm asking you, can you find such an interpretation? Now, that's the same as asking, can you find a property and a relation that makes those propositions true? But then suppose you try hard to find one, but you don't succeed for some reason. And at the same time, you try to make a proof and you also don't succeed. So that doesn't give you an answer to whether this argument is valid or not, right? So we'd like to have a way of saying, for all possible properties and relations, there doesn't exist one such that the premise would be true and the conclusion false. That requires that we quantify over all properties and relations. Now, in order to do that, we need set theory. We cannot answer questions like that without set theory. So we can do quite a bit of logic. In fact, hey, we've done enough logic to build up to the point where we're at without using a formal set theoretic foundation. Because if we'd done that, then our whole edifice would be circular, right? So we've built all the way up to here without using set theory as a foundation for logic. And then when we reach a certain point in set theory, then we're going to use that set theory to clean our acts, so to speak. Not that what we said is wrong, but we're going to make it more precise to answer questions in logic that we haven't been able to answer so far. Okay, so let's talk a little bit more about those relation symbols, right? The relation symbols that are interpreted with respect to a particular domain are going to be interpreted, as I was saying, as a set of ordered pairs. And with the axiom of separation, we're going to make sure that we're just going to keep the ordered pairs that make the relation true, right? So the pair xy such that Rxy is true. So this is the axiom of separation, gives us the direct connection between the language and its semantics. So we see that the power set of the Cartesian product of the domain with itself is going to form the set of all possible binary relations over the particular domain. Now, again, we're talking about the extension of relations, not about their intention, whatever that might be. Okay, so that's the sense in which we become in a position to quantify over all possible binary relations. So a relation from that point of view, suppose we don't want to take relation between objects of a universe of discourse, but say between two different things, maybe between students in 310 and times, maybe times it takes to complete an assignment, right? That maybe those two things are subsets of one other set, the universe of discourse, maybe not, it doesn't matter. But if we want to define in general a relation between things in the set A and things in the set B, we're going to see that the relation is just a subset of the Cartesian product A cross B. So that is to say, it is just some of those ordered pairs whose first member is in A and second member is in B. And there's going to be as many distinct relations as there are elements in the power set of the Cartesian product A cross B. So hopefully that makes some sense. Now, at this point in a set theory course, they would make you prove all sorts of theorems about reflexive relation, transitive, symmetric, anti-symmetric, and all that. But we've already studied all of that as part of predicate logic, so we don't need to be bothered, and we can just move forward and just say a little bit more about equivalence relation and why we care so much about equivalence relations. So an equivalence relation, as we saw, it's a relation that's reflexive, symmetric, and transitive. Now, on any particular set A, there's going to be two equivalence relations that are called trivial. Why? Because they are so very simple. The first is the set of ordered pairs that contains all the ordered pairs such that the first and the second member are exactly the same. Because of that, that relation is often called the identity relation on A, right? You could see that, of course, if all your ordered pairs are such that the first member is the same as the second member, that really captures the idea that for all x in A, x equals x. So that's the first equivalence relation. Why is it said to be an equivalence relation? Because, well, the identity relation is reflexive, symmetric, and transitive, as we already studied. And the second one is the entire Cartesian product that contains all the possible pairs of objects in A and B. And this, I'm not proving it, but I'll just ask you to think about it intuitively a little bit, and I think you're going to be able to convince yourself that between any two objects, there's going to be an arrow in both directions, and therefore it has to result in an equivalence relation. But those are the two trivial equivalence relations on a set. There might be some that are not trivial. So here, imagine that all the dots are part of one and the same set, okay? And what I've done here is that I've drawn arrows to capture the idea that some objects relate to other objects. So here, if we take the first dot in the first part, it has an arrow to itself, an arrow to the left, bottom left, and to the bottom right, right? That means that this object is related to those three things, but it doesn't relate to any of the other ones on the right, okay? Now notice that here the relation is reflexive. Try to convince yourself of that just by inspecting all the arrows. It's also symmetric and also transitive. Okay? And when we have those three things, reflexive, symmetric, and transitive, the dots form clusters. Here we have three clusters of dots that are all related to each other, but to none of the dots in the other cluster. Okay, so this is the idea. So suppose we look at, I don't know, the third cluster, and I decide to remove the arrow on the top. Now, would the relation be an equivalence relation after I remove this arrow? No, because that dot wouldn't relate to itself, right? So the relation wouldn't be reflexive. So if I remove a single arrow in that diagram, it's not an equivalence relation anymore. And moreover, if I just add one more arrow, say between this element here and this element here that are in different clusters, again, the result is not going to be an equivalence relation. Why? Well, because the reverse arrow is not going to be there, for example, so it's not going to be symmetric. Maybe you'd like to add this arrow here to make it symmetric. But then you're going to need to start to add more arrows to keep transitivity. And in fact, you're going to add so many arrows that those two clusters here are going to coalesce together. Okay? So that's really cool because those equivalence relations take a set and form a bunch of clusters out of them. Now, there's a technical term for those clusters, and that's an equivalence class. Okay, so take any element A of a set X. Okay, and imagine we have an equivalence relation on the set X. We're going to call that R. Then we're going to define a set. A slash R is going to be the name for that set. It's meant to be read as a whole. And it's meant to be read as the set of objects equivalent to A under R, or the set of objects that are in the same cluster as A, right? So that's going to be the set of objects in X such that A relates to X, basically, right? So that set here is the set of all objects that A relates to. So that means that this is a cluster. Instead of writing A slash R, it's often common to use square brackets surrounding A with a subscript R to talk about A's equivalence class. Okay, so if we go back to this slide here, we have one cluster, two clusters, three clusters, right? Each of them, so take the item at the top, it relates to those four other objects, so those five objects together form an equivalence class. And now we might want to form a set that contains all the equivalence classes. Here it would contain the three equivalence classes, and we're going to write it X, this time the set X, which we're clustering, slash R, which denotes the set of all equivalence class. So X slash R is the set of A slash R such that A is a member of X, the set we're clustering. Very often, X slash R is read X modulo R or simply X mod R, or the quotient of X by R. Now, in this course, I'm not going to talk a lot about that, okay? That's a super interesting topic, but I really want to get to functions and inductions, which I think are more important for this course, and we don't have a lot of time left. So we're going to not say too much about that, but for those of you who are in math, who are going to take a course in abstract algebra, for example, or in graph theory, you're going to be using equivalence classes so much, and you're going to write X mod R so much, and you're going to deal with that a lot. But for now, I'm not going to go ahead and say more about that. I just want to say a few Actually, okay, I'll say a few basic things that are relevant here. The first is that for those clusters that I was talking about, there's a technical term. Um, so let's introduce the concept of a partition. So, oops, I'm sorry. Okay. So suppose we take a set X. A partition of X is a set of mutually disjoint non-empty subsets. Okay. So we have a collection of sets, and each of those sets in there, they don't overlap. So their intersection is empty. That's what it means to be mutually disjoint. And furthermore, every set in that collection has to be non-empty, and every element in that collection has to be a subset of X. So you can think of the sets in that collection C as being those clusters that, or those equivalence classes that I was talking about. But at this point, we would be jumping a bit ahead of ourselves if we were to do that. But in any case, that's where we want to go. And the idea is that those sets in that collection, not only are they non-overlapping, but if we take all of them together, it includes every element of X. Right? So every element of X has to be at least in one set in that collection, but will be in at most one set in the collection. And sometimes people call that a set that is jointly exhaustive and mutually exclusive. All right? And then we can, after defining a partition in that way, then we can say the following, the following fundamental, that's my phone, the following fundamental theorems that relate partitions and equivalence classes. So to every partition, there corresponds an equivalence class. I give the short proof in the notes. It's very easy. The idea is that if you have a partition, each set in the partitions, you can think of it as a cluster, which is an equivalence class. And from there, you get an equivalence relation. And vice versa, that's often called the fundamental theorem on equivalence classes. If you start from an equivalence relation on a set, then the set of all of its equivalence classes is going to be a partition, that is to say, a collection of non-empty, mutually disjoint, and jointly exhaustive sets. I'm not proving any of that, but again, if you were to take graph theory or abstract algebra, that would really be important. Now, I just want to introduce one last thing for today, and is the idea of an inverse relation. That's going to be important for us very soon, because we're going to introduce functions as being a particular type of relation next time. And of course, there's an important concept associated with functions, namely inverse functions. And inverse functions are going to be a particular kind of inverse relation. But let's get started with it, just for the case of relations. So if you take a relation like being larger than, there's normally one other relation that is naturally associated with that relation, namely being smaller than. And one of the important property of those two relations is that for all x and y, if x is larger than y, then y is smaller than x and vice versa, right? So we just take the two arguments n, x, y, and we rewrite them in the opposite order. And that's characteristic of inverse relations. So let's just have the definition. Let R be a relation, that is to say, R is a set of ordered pairs whose first members are in A and second members are in B. So we have a relation. And the inverse relation of R, which is denoted R superscript -1, that is a subset of the Cartesian product of B cross A, where the pair XY is in B cross A if and only if the pair YX is in the relation R. So it tells you if today is earlier than tomorrow, then tomorrow is later than X. And that's all there is to it. So that completes the material for this week. I hope you're going to like it. In terms of the assignment, there isn't as much on the second part in this lecture that we're doing now. Um, but it's still important material, especially Cartesian products. We're going to revisit those very much. But in the meantime, I'll let you work on power sets quite a bit. And next week, we're going to talk about functions. All right. So on that note, have a great weekend. Bye-bye.